Welcome friends. Today 16th of September 2018 Sunday. So here you go with our set 10. This set contains of questions from perturbation theory. So let's begin. So first question, a one-dimensional simple harmonic oscillator with Hamiltonian H0 equals to p square by 2m plus half kx square is subjected to a small perturbation h1 equals to alpha x plus beta x cube plus gamma x to the power 4. The first order correction to the ground state energy is dependent on. Okay, so we are given Hamiltonian and the perturbation. Okay, so first order correction to the ground state is given by EG1. It is denoted to denote this one represents the first order correction to the ground state. So expectation value of h1, so integration of psi g star h1 psi g dx. Okay, now it is a simple harmonic oscillator, one dimensional harmonic oscillator. So the wave function for one dimensional harmonic oscillator is m omega by pi h cut to the for ground state. This is ground state wave function for simple harmonic oscillator one dimensional. M omega by pi h cut to the 1 by 4 to the minus m omega 2 h cut x square. So basically if you write as x square is there, so it's basically an even function. So EG1 means first order correction to the ground state equal to alpha average value of x, expectation value of x, beta x, expectation value of x cube plus gamma expectation value of x to the power 4. Now as you can see, expectation value of x and x cube, this is 0 because x and x cube are odd functions, but this x to the power 4 is even function and the wave function is also even, so it will produce some non-zero terms. So it should depend only on gamma because the x to the power 4 term is associated with gamma. So option D is the correct option. Next question, a hydrogen atom in its ground state in the presence of a uniform electric field E equals to E naught z cap, the leading order change in its energy is proportional to E0 to the power n. The value of the exponent n is. Now E equals to E naught z cap, so electric field is in the z direction. Okay, suppose this is z direction. Now therefore the perturbation becomes, because look, this is not energy term, this is electric field, so we have to consider the corresponding Hamiltonian. So the perturbation means some energy kind of thing. The perturbation is h1 equals to E naught into z, because electric field is in the z direction. Therefore the first order correction to the ground state energy is 0 because the expectation value of z is an odd function. So as you can see, expectation value of z, this term is 0. Now we have to find out the leading order change in its energy, leading order term. So next this is the first order correction. Now next we will calculate the second order correction. So for ground state n equals to 1, L equals to 0, M equals to 0. So E1 0 0, this 2 represents the second order correction. So as you know from the formula that phi NLM Z phi 1 0 0 square E1 0 minus En 0, where NLM is not equals to 1 0 0 because means the value of n should not be equal to 1 and square is there, so E square E naught square comes out. We need to compute all the matrix elements of Z between the ground state and the other hydrogen state to calculate this term phi NLM Z phi 1 0 0. Now if we calculate this, so this is a tedious calculation, you will get a term like this, but in your exam you don't need to calculate this. You can easily say it from this matrix that on E naught square term will come outside, and as this term will always give positive, okay, and this term is negative, so a negative term is coming. And what you need to know, what will be the power of E naught. So as you can see, the power of E naught is 2. So without calculating this term, you can say the exponent is 2. Okay. Now coming to the third question, a particle is confined in a box of length L. Okay, so this was the box. Okay, so this length is L. Now if the potential V0 is treated as perturbation, so V0 has been given as perturbation, including the first order correction, the ground state energy is. So if there was no perturbation, then the ground state energy would be pi square h cut square by twice m L square. Now what changes or what additive terms are added due to the perturbation, that we have to find out. Okay, so let's calculate the first order correction. Ground state wave function, as you all know, root over 2 by L sin pi x by L. Okay, and this is the perturbation. The perturbation is shown in this figure, which is extending from 0 to L by 2. The first order correction, energy correction term. So what does it mean, this term? E0 means ground state energy and this 1 means first order correction. So 0 to L by 2 psi star psi dx. Psi star psi means 2 by L sin square pi x by L, and V naught is a perturbing term is multiplied here. This is the formula. As you can see, this is the formula for first order correction for non-degenerate perturbation theory. So we are taking out V naught by L outside, and 2 sin square pi x by L equals to 1 minus cos 2 pi x by L. So if you carry out the integration, it's basically simple integration of class 12. So if you carry out the integration, I have illustrated the solution. You can check it out, and you will get V naught by 2. So this term V naught by 2 is coming due to the perturbation. So including the first order correction, the ground state energy become, so this was the original energy. Now due to perturbation, some additive term is added here, V naught by 2. So this is the cumulative or ultimate energy, ground state energy, including the perturbation effect, and this is matching with option D. Okay, next question number 4. A particle is confined to a one-dimensional potential box with the potential V of x equals to 0 when 0 less than x less than a and infinity otherwise. So it's basically one-dimensional infinite potential well. If particle is subjected to a perturbation within the box, W equals to beta x. So this is the perturbation where beta is a small constant. The first order correction to the ground state energy is, okay, so for a particle in one dimensional box, the wave function is given by this one I have already discussed. Okay, now for ground state energy you have to put n equals to 1. So putting n equals to 1, we get root over 2 by s sin pi x by s. So this is the ground state wave function. Now this is the perturbation given. So the first order energy correction in the ground state energy becomes psi 1 w psi 1. So psi n star w psi 1 dx. So we just replace the value of w psi 1 psi n star to evaluate this integration. Upon evaluating this integration, we get a beta by 2, and this is matching with option C. So option C is the correct option. Now question number 5 and 6, common data is given. To the given unperturbed Hamiltonian, this is unperturbed Hamiltonian, we add a small perturbation given by epsilon into this matrix, where epsilon is a small quantity. The ground state eigenvector of the unperturbed Hamiltonian is, remember one thing, or you should notice this, that they are not asking about eigenvalues, they are asking about eigenfunction or eigenvector in question number 5. And in question number 5, they are asking that a pair of eigenvalues of the perturbed Hamiltonian using first order perturbation theory is. So here we have to calculate the eigenvalues taking the perturbed Hamiltonian. Okay, so let's discuss the solution of question number 5. So unperturbed Hamiltonian is given like this. This is unperturbed Hamiltonian. Now to find the eigenvalues, as you know, this is straightforward. So a minus how to calculate a minus lambda equals to 0? You have to find out the roots of that equation, or means value of lambda. So if you calculate the eigenvalues, you get 2, 3 and 7. You can see the process, you can see the calculation, you can check it out. Now part-up Hamiltonian given by this is already given. Therefore eigenvectors corresponding to the eigenvalue of the unpartupped Hamiltonian means 2, 3, 7. These are the eigenvalues, and the corresponding eigenvectors are phi 1 equals to 0, 0, 1, phi 2 equals to 1 by root 2, 1 minus 1, 0, phi 3, 1 by root 2, 1, 1, 0. So we have to find out the perturbation eigenvector of the unperturbed Hamiltonian. So the unperturbed Hamiltonian is eigenstate of the unperturbed Hamiltonian. For ground state it is 0, 0, 1. So option C is the correct option. Now if you want to calculate it, I have shown the derivation in the next page. Okay, this is lambda equals to, for lambda equals to 2 means for ground state we have calculated this. So how we are getting 0, 0, 1, it is illustrated in this page. You can check out the calculation. I am not explaining it, you will understand it. Okay, so this is the calculation, you just check it out how we are getting 0, 0, 1. Okay, straightforward. Now coming to question number 6, for first order correction to energy. So this one we have to calculate for perturbed one. So phi 1 HP phi 1. So we have calculated phi 1, phi 2, phi 3. We can calculate it using this same tricks. Okay, so I have just shown phi 1 and phi 2, phi 3 can be similarly identified as this. So E1 prime means first order correction to the ground state energy. So if you evaluate the matrix multiplication, you will get epsilon. For first order correction to the second first excited state, E2 prime, you will get 0, and for third one you get twice epsilon. So E1 becomes, so 2, 3, 7, these were the eigenvalues for the unperturbed one, means without perturbation. Now due to the perturbation, some additive terms are added here. So epsilon is added with it, and 0 is added with it, and 2 epsilon is added with it. Now we have to find out pair of eigenvalues. Now we have to check out the option for this, because not all the three options, eigenvalues are given, only 2 eigenvalues, pair of eigenvalues is given. So as you can see, the pair of eigenvalue is C, 3 and 7 plus 2. So we are getting that 3 and 7 plus 2. So option C is the correct option. Now coming to question number 7. Consider a system in the unperturbed state described by the Hamiltonian H naught equals to 1, 0, 0, 1. The system is subjected to a perturbation of the form H prime equals to delta, 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 delta. When delta is much, much less than 1, the energy eigenvalues of the perturbed system using the first order perturbation approximation are. Okay, so this one, to solve this one, we have to use matrix method. Okay. Now energy eigenvalues corresponding to the unperturbed Hamiltonian. So first we are calculating the energy eigenvalues for the unperturbed one. For the unperturbed one, we get the energy eigenvalues 1, 1. So it's basically degenerate. So and as you can see, it is only diagonal terms are remaining, so it is diagonalized. Now H0 d equals to H0, and Hj, if the Hamiltonian, unperturbed Hamiltonian I diagonalized, then in that basis the perturbed Hamiltonian will also be diagonalized. Okay, so Hd prime equals to H prime. Therefore the Hamiltonian becomes total Hamiltonian H0d plus Hd prime. So this is H0d and this is Hd prime. So if you add them up, you will get 1 plus delta, 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 1 plus delta. Now to find the energy eigenvalues, so we have to find out the first order energy eigenvalues of the perturbed system. So the Hamiltonian of the perturbed system is this. Now to find the energy eigenvalues, we use the same tricky formula. A minus lambda I equals to 0. So and finding the characteristic roots. So if we evaluate this, so this is not metric, this is determinant. then if you equate it to 0, you will get lambda equals to 1 plus 2 delta and 1, and it is matching with option A. Look, I have not shown here the calculation. You can see it here. I have done in rough work. So if you carry out this, you will definitely get the answer. You can check it out here. Okay, I have shown you the calculation. You just check it out. Next, question number 8. The normalized eigenstates of a particle in a one-dimensional potential well V of x equal to 0 when 0 less or equals to x less or equal to a and infinity otherwise are given by psi n of x equal to root over 2 by a sin n pi x by a, where n equals to 1, 2, 3. The particle is subjected to a perturbation v prime x equal to v naught cos pi x by a for 0 less equal to x less equal to a by 2 and 0 otherwise. The shift in the ground state energy due to perturbation in the first order perturbation theory is. So this is also a straightforward question. We have already discussed this type of problem. So let's see. So the first order correction in the ground state is psi 1 v prime x psi 1. So normal integration, and we will get the answer 2/3 v naught by pi. So some clumsy integration is there, and it is matching with option A. Okay. Question number 9. A particle of mass m is confined in an infinite potential well v of x equal to 0 and 0 less than x less than L and infinity otherwise. It is subject to a perturbing potential Vp of x v naught sin 2 pi x by L. So it's basically sinusoidal type perturbation within the well. Let ES should be E1 and E2 be correction to the ground state energy in the first and second order in V naught respectively. Which of the following are true? This is a very good question. It came in GATE 2010. The perturbing potential is given by this Vp of x equal to v naught sin 2 pi x by L. In an infinite well, the wave function is this 2 by L root over 2 by L. This is not 1, this is 2 by L sin n pi x by L. Now the correction to the ground state energy in the first order E1 1. Okay, this one E1 1 and equals to psi 1 Vp x psi 1 0 to L 2 by L sin square pi x by L v naught sin 2 pi x by L. So it should be sin square pi x by L. Yes. So sin square pi x by L. So 2 sin square pi x by L equal to 1 minus cos 2 pi x by L. Okay, v naught by L are coming outside, and sin 2 pi x by L dx remains outside. So sin 2 pi x by L dx minus cos 2 pi x by L into sin 2 pi x by L dx. So this term produce 0, big 0. This term will also produce a big 0. So ultimately this term is vanished. Next, correction in the second order is this. Now as you can see, the numerator is always positive. Okay, you can check it out here. But E1 this ground state energy and EM are the excited states. Now excited state energy are definitely will be higher than this ground state energy. So this denominator term is always negative. So effectively the second order correction will be negative. And so first order correction is 0 and the second order correction is negative. And it is matching with option A. Next, question number 10. So this is the last question of this set. An unperturbed two-level system has an energy eigenvalues E1 and E2 and eigenfunctions 1, 0, 0, 1. When perturbed, its Hamiltonian is represented by this. So almost everything is given. So this is basically a very simple problem. So given perturbed Hamiltonian is this. So this is the cumulative Hamiltonian for the whole system, perturbed system. So we can separate it out in terms of unperturbed Hamiltonian plus the perturbation. So if you try to separate it out, we can see that how can we write the perturbed Hamiltonian in terms of the diagonal elements. Okay, so if you write it H0 plus H prime, so this is the perturbation term, this is the unperturbed Hamiltonian. Okay, phi and phi 2 the base vectors are given 1, 0, 0, 1. Therefore, the first order correction energy E1 means phi 1 H prime phi 1. This is the common formula, first order energy correction. So 1 0 is 0 A star 0 1 0. So you get 0. So the correct option is 0. Option D. Option D is the correct option. So with this we have completed set 10. So completed set 10 means 10 into 10 100 solved questions. So till today we have discussed 100 solved problems of physics. What we did, we discussed problems from NET exam, problems from atomic molecular physics, perturbation, and many other types of problems we have already discussed. I will give the link of all the set videos in the description. You can check it out. Look, basically in every year, I'm talking about recent years, from 2017 down to 2006, 2017 to 2011. Every year one question definitely came from this perturbation theory, and in 2018 GATE physics paper, no question came from perturbation theory. So there are high chances that one question will definitely come from this perturbation theory part in GATE 2019. So solve problems on it, and this video will also help you in this regard. Here I have covered almost all the perturbation problems from GATE 2006 to GATE 2017. So work hard, and don't forget to like, share and subscribe before leaving. And if you have any question, confusion or query, you can comment down below. And before leaving, don't forget to press the bell icon if you have not done till now. And finally, thanks for watching.